Hi friends, now we'll see one more discrete probability distribution, that is Poisson distribution. First one is a binomial Poisson and multinomial distribution. So we have seen already in a binomial distribution, if n is the number of trials, p is the probability of success, x is the number of success required, then probability of capital X equal to small x. If x is still said to be binomial distribution, then capital X equals to p of n comma p, or n comma p are the parameters. Now, so the mean of the binomial distribution is NP and the variance is NP cube. Standard deviation is square root of NP cube. Now we'll see the what is the special case of the Poisson distribution rather than binomial distribution. Right. So the Poisson distribution is a discrete distribution, statistical distribution that shows how many times an event is likely to occur within a specified period of time. It is used for independent events which occur at a constant rate within a given interval of time. A Poisson distribution is a measure of how many times an event likely to occur within X period of time. Now, how that Poisson distribution is varying from binomial? Simply, the Poisson distribution is limiting case of binomial distribution. So we'll go with the Poisson distribution when p is very small, n is very large, so that np is finite. So np equals to lambda, so which is called a Poisson parameter. So it was named after the mathematician Simon Dennis Poisson. So the special the Poisson distribution is the limit case of binomial distribution. So we'll go for the Poisson distribution when p is very small and n is very large, such that np equal to lambda is finite. Then it will go for the Poisson distribution. Now, so let capital X be the discrete random variable that represents the number of events observed over a given time period. Let lambda be the expected value average of capital X. If X follows the Poisson distribution, then the probability of observing X events over the time period is P of capital X equals to small x equals to e power minus lambda into lambda to the power of x by x factorial, where lambda is the Poisson parameter, lambda equals to n into p, where n is the number of trials, p is the probability of success. Here p is very small, n is very large, so x is the number of success required. Then the probability function of the Poisson distribution is defined by p of capital X equal to small x equal to e power minus lambda into lambda to the power of x by x factorial, where x equals to 0, 1, 2, 3, 4, so on. So lambda is the NP, where n is the number of trials, p is the probability of success, and E is the Euler constant. So 2.7182 is the value. Now, what are the conditions for the Poisson distribution? So an event can occur any number of times during a time period. So first condition. Second one is events occur independently. In other words, if an event occurs, it does not affect the probability of another event occurring in the same time period. Third one, the rate of occurrences is constant. That is, the rate does not change based on the time. So the fourth one is the probability of an event occurring is proportional to the length of the time period. For example, it should be twice as likely for an event occur in a 2 hours time period than it is for an event to occur in a hour period. So the probability of an event occurring is proportional to the length of the time period. So now we'll see what is the mean of the random variable when it takes the Poisson distribution. So the mean of the Poisson distribution, E of x equal to, we have the formula x into p of x. So x takes the random variable Poisson distribution, random variable x takes the Poisson distribution. Then summation x equals to 0 to infinity x into e power minus lambda into lambda to the power of x by x factorial. So is equals to x equals to 1 to infinity. So x into e power minus lambda into lambda to the power of x by x factorial. Since x equal to 0, the term itself is going to be 0. Now, if I'll take the summation depends on the x values, not on the lambda. So I'll take this one e power minus lambda into lambda. If I'll take outside, then x equal to 0 and 1 to infinity lambda to the power of x minus 1 by x minus 1 factorial. So factor e power minus lambda and lambda 2. Now lambda into e power minus lambda equals, if I expand this one, x equal to 1, lambda power 0 by 0 factorial plus lambda power 1 by 1 factorial, lambda square by 2 factorial plus lambda 3 by 3 factorial, so on. It's a Maclaurin's expansion for e power lambda, then lambda into e power minus lambda into e power lambda. So lambda is the mean of the Poisson distribution. So mean lambda is the parameter, then mean of the Poisson distribution is lambda itself. Now we'll see what is the variance. So we have the formula for variance is equals to expectation of x square minus expectation of x whole square. Now we'll see this one I'm writing expectation of x square minus expectation of x whole square. I'm writing as expectation of x into x minus 1 plus x minus expectation of x whole square. Like that, how we are doing it with binomial. Same here also we are writing the expectation of x square as expectation of x into x minus 1 plus x. Now we know that the mean of the Poisson distribution is lambda, then expectation of x into x minus 1 plus lambda minus lambda square. Now we'll find what is the value of expectation of x into x minus 1. So expectation of x into x minus 1 equal to x equal to 0 to infinity x into x minus 1 e power minus lambda into lambda to the power of x by x factorial. When x equal to 0 and x equal to 1, the terms are themselves are 0. So summation will start from x equals to 2 to infinity x into x minus 1 e power minus lambda into lambda to the power of x by x factorial, or x equal to 2 to infinity e power minus lambda to the power of x by x minus 2 factorial. So divided by the x and x minus 1. Now lambda square into e power minus lambda, if I'll take outside, x equal to 2 to infinity lambda to the power of x minus 2 by x minus 2 factorial. So lambda square into e power minus lambda plus lambda power 1 by 1 factorial square lambda square by 2 factorial plus lambda cube by 3 factorial. So it is the expansion of e power lambda. So lambda square into e power minus lambda into lambda. So expectation of x square is equals to the expectation of x into x minus 1 value is lambda square. If I substitute this one, then variance of x equal to this value is lambda square plus lambda minus lambda square getting cancelled. Lambda is the variance of the Poisson distribution. So the both expected values of the variance of the capital X is equals to be lambda. So the mean and variance of the Poisson distribution lambda itself. But when I'm moving to the binomial distribution, the mean of the binomial distribution is NP, variance is NPQ. But whereas the Poisson distribution, the mean and variance of the Poisson distribution are same, that is lambda itself. Thank you.